Hello, everybody, and thank you for being here. My name is Alireza, and I'm doing a PhD at Technical University of Denmark. So, as a short break, let's say Happy Nowruz, which is Persian New Year. This is the first day of the New Year for Persians, and all these countries that you see on the map are celebrating the New Year. So, Happy Nowruz, and this is a symbol of the New Year in Iran, which is called Haftzin, which is 7 things that it starts with the letter S, like seep, which is apple, or I don't know, sombol, which is a kind of flower, and all of these are a symbol of something. Some of them are a symbol of health, some of them are a symbol of wealth, power, anything. So I wish you all happy Persian New Year with health, wealth, and everything. So let's go for the main topic. First, this is the ID card, the core digital manufacturing technologies. In my project are simulation and big data, and my supervisors are Guido Tosello, Matteo Calaun, Jesper Hattel, and Murat Kulaci, are all from Technical University of Denmark. The industrial partners of my project are Carmo, which is a small plastic injection molding company in Denmark, and Novo Nordisk, which is, I think, the biggest company in Europe now. The key industrial applications of my project are quality prediction and process optimization of manufacturing. So, the thing that I want to tell you today is the project that I've been involved during past 3 months in UK. So I was to University of Bradford, UK for my external research stay. And the thing that we made there, I don't know if it is clear, it's a plate including 100 microneedles on the top, and all of them are different in height and aspect ratio. Some of them are longer, some of them are shorter, some of them are thinner, some of them are thicker. So all of the 100 microneedles are different. And the application of this small thing is to apply medicine under the skin. So consider that something like COVID happens again, and we need a lot of drug that can be applied easily and very fast. This device can be useful. In this case, we can have medicine on these microneedles, like pre-prepared, and with a small push on your arm, this can be applied, and it delivers medicine to your body without the need to any nurse or anything. You can do it yourself. So it's very easy. And the material that we use there to manufacture this thing were 3: polypropylene, POM, and polycarbonate ABS, which are a combination of crystalline and amorphous plastics. And this is the machine that we use. This is a micro-injection molding machine, which is probably one of the most accurate micro-injection molding machines. And this is obviously different with a regular injection molding machine. And we used an accurate 3-part mold, which you can see here. This is the insert of the tool, and this is the other side of the mold. So I will explain a bit more about this tool later on. And in this case, we had a lot of sensors, extra sensors in mold and on the machine to measure like the process even better. And also we did some measurements on the final products, which were microneedles. For example, you can see a microscope here that measures the flatness of the surface of the microneedle plate, like this. It is important because the surface should be flat. If it is warped or something, it cannot deliver the drug properly. So we measure also the surface flatness, and then later on we try to predict the flatness based on machine learning algorithm that we train. Also, the other thing that we measure is the height of the needles and the roundness, or let's say the diameter of the tip of the needles, using this device, which is a camera, and the part will be placed here, and this camera will measure the height and everything of the microneedles. And here you can see a picture of those measurements of that camera, which are the microneedles. And as you can see, they are a bit different in size. And this software measures the height of them based on the bottom line that we specify, that we pinpoint here. And it will measure the tip height from this bottom line. Also, it measures the roundness of this tip, so that we can realize that how sharp are the needles. So the input factors that we considered to be studied during that study were melt temperature of the polymer, mold temperature, injection speed, packing pressure, and velocity switchover points. So 5 factors to be studied. And also the objectives of that study were the height of the needles, the diameter of the tip, the plate's flatness, as I told you, the part's weight, and flash, which is a defect in injection molding parts, and bear marks. Most of the quality measurements are done in UK. Anyway, I prepared these conveyors using 3D printing to convey all the parts that I manufactured and collected back to Copenhagen in case that we need any more measurements. So I don't know how much you know about design of experiments, but we adopted a CCD type design of experiment because consider that we have 5 factors to be studied and we want to have 5 levels for each factor. For example, in case of melt temperature, we want to consider like 180, 190, 200, 210, and like 5 of them to see if we increase the temperature, what happens in the quality of the product. So 5 factors and 5 levels. In this case, we are supposed to have almost 3,100 experiments. And it's impossible to do that much experiments because it's costly, it's time consuming, it's not possible. So we use design of experiment to reduce the number of tests as much as possible, at the same time keep the quality of the data set as much as we can. So we used CCD type of design of experiment, which gives us 32 experiments for each material to be done. As I told you, we have 3 materials. So 32 experiments out of 3,000, which is very much less. 32 experiments for each material, and I collected 12 parts per test set. So we have 32 crossed by 12 for each material collected. And a lot more not collected, because if you're doing injection molding, you cannot collect all the parts. Some of them are waste, and you need to wait for the first 3 or 5 injections for the machine to be stabilized, and then start to collecting parts. So every material, every polymer has these coefficients, which are PVT and viscosity coefficients, and they are like fingerprints for each material. For every single different polymer, we have different coefficients here. So why I'm telling you this? Because we are going to use machine learning to predict the results of injection molding without having need to actually do the experiments. So in this case, we will gather a lot of data, a large data set of experiments, and then we give these coefficients and those 5 things that I told you we are going to study, like melt temperature and so on. We are giving these coefficients and those design parameters to the machine learning algorithm, and after training the algorithm, it will give us the results for any unknown material that we ask the algorithm. So consider that we are facing a new material that the algorithm doesn't know, but we want the results of that material. We don't need to do those time-consuming and costly experiments. We just simply ask the algorithm to give us the results. So it saves a lot of money, a lot of time, and it's simply much easier. So the challenges of doing micro-injection moldings are this. For example, this is the insert of the tool. So we have like an insert with 11 smaller inserts, which make the cavities for those micro needles. And since they are very small, the needles can easily break into the cavities. And if they break in there, it's impossible to continue injections because the material cannot go in cavities. They are blocked. And it takes almost, based on my experience, it takes at least half a day to 1 day to open up the mold, clean it. With this process, as you see, these are the cavities. They are very small. And something can break in them, as you see. If it is clear, the material is stuck in there. And it's really a chore to open the mold, clean them, and install the mold again. You should use ultrasound bath to put the insert in there. And then after 3 hours, take them out, clean them, and do like microscopy observation to see if anything is still in there. The black thing is the material stuck in the mold, and after cleaning, as you see, it's totally clean. So you should do it for all the 11 inserts, and every one of them take at least 5 to 10 minutes, and consider that how much time we need to clean the mold. So, as I told you, it's very costly and time-consuming to do all these things by experiment. The thing that we want to obtain is a machine learning algorithm that gives us all these results very simple. This is the essence of my project, basically. And, come on. And last but not least, I want to say thank you to the Bradford team, MNT Lab guys, that doing this project without them would be impossible. And also I want to thank to Guido, because he provided me this opportunity to go there and work with these amazing people. Also, thank you all for listening to me, and I would be happy to answer any questions if you have. Thank you so much.